Another session of the mixed signal IC design course. So in the last class we started our discussion on digital to analog converter architecture. So we have saw some basics like how generally DAC generate analog output voltage. We spoke about 3 different methods, and we saw about 2 methods in a bit detail. And then we started off, we also mentioned that the digital input code need not be always in a binary format. There are different formats through which we can present the input digital code and thereby convert the digital to the data from digital to analog. And then we started off with the simple and the very basic digital to analog converter, which is a resistor string DAC. So there we saw that we use around 2 to the power of n identical resistors and switches, and the output will be tied like this, what you are seeing on the screen. This is pretty straightforward because after every resistor we will tap the output voltage, and that will be controlled by a switch directly. So in this case we might need some like some other control logic in order to control the switches, but we saw that one drawback about this is at every output will be connected to all the switches at every time, and one switch will be on at a specific instant. So the large capacitive load which is presented at the output may cause may affect the speed. That is one concern what we raised, and there is one solution for that is to present the digital input data in a binary fashion. That is what we saw later. But in general, for very basic applications, generally we can go for this type of DAC. Again, by looking at the need, before incorporating, we should also see the need of our specific application. Now, coming to this alternative where we keep binary switch array, we saw that the output will be connected only to through the binary switch array. Output will be connected to less number of transistors, so the capacitive load is actually reduced a lot, thereby conversion speed will be good. But in general, both for the simple resistor string or with the binary switch resistor string, one disadvantage, especially when we look for minimum power in an IC form, is every time the resistor is connected to supply, and this will be the resistors will be drawing current. That is one drawback of this type of data converter, right? The current will be flowing through all the resistors at all the times, right? Now today what we'll do is we'll continue this discussion, but now we need to look upon, we need to understand about the possible non-linearities of this DAC, because we discussed about the specifications DNL and INL, which we know will give you the overall non-linearity of a DAC. So we'll look in such details. Before that, let us start with a simple design question. The question is this: design a 3-bit resistor string ladder using a binary switch array. One second, yeah. You can note down this question. A 3-bit binary string DAC. This is 3-bit using a binary switch array. Assume that Vref is equal to 5. Reference voltage is given as 5, and the maximum power dissipation of the converter to be equal to 5 milliwatt. Reference voltage is 5 and maximum power dissipation is 5 milli, but in that it is not given that not including the power required by the digital logic. So the entire 5 milli can be taken for the DAC part alone, excluding the logic circuitry part. The question is to design. So design in the sense we should design the component values, as in this case it is resistor values, and also determine the value of the analog voltage for each possible digital input code. Right. It's a pretty straightforward question. What we can do is you can I'll just tell you how to proceed with this. You can do along with me. Right. So the conditions which or the constraints given here is the power constraint. So we have a reference voltage given which is equal to 5, then the power dissipation, the maximum power dissipation is given as 5 milliwatt, right? Now we know that this power dissipation is equal to the total power, right? The total power is the total supply, the voltage into the current. So I can take it as VDD. VDD is nothing but this reference voltage into the total current flowing in the circuit, I total, right? So from this we'll get the information about the maximum current which is available. So I total is equal to power dissipation divided by reference voltage. So what we have is 5 milliwatt divided by reference is 5. That will give you 1 milliampere as the total current in the circuit. So when I say total current, for a 3-bit DAC, we know 2 to the power of 3, 8 resistors will be there, and the total current flowing through all these resistors is equal to 1 milliamp, right? So if you look at the this is the circuit, right? So this is VREF, this is 5, this is resistor 8, two and 1, right? So given that it is binary switch array, so this is how it is connected. This is how the circuit looks like, and we discussed about this in the other day as well. And here it will be, all the control will be D0, this will be D1, and this control will be D2, right? So this is D2, this is D2. I am not drawing the complete details. Now what I need to find first is, when I say design of this resistor string ladder DAC, we need to find the value of the resistor. There are 8 resistors, the total current we know, supply voltage we know, so the resistance value, so I can write that the total resistance will be equal to VREF divided by I total. So what is the single resistance value for this? What is the single resistance value? VREF is 5, I is 1 milli, so the total resistance is equal to 5k. Yeah, it is 5k, Durgesh, correct? So the individual resistance, so R1 to 8 is equal to, there are 8 resistors, so 1 by 8 into 5k, that is equal to, what is the value? 1 by 8 into 5k, it is what is individual resistance value? R1 to 8. Yeah, it is equal to 625. 625 ohms. This is the resistance value. Alright. Fine. Now, once the resistor value is done, that means the design part is over. What we have rest is only switches, and we need to have a control logic to control the switch with all the bits, MSB through LSB. Now the second part of the question is determine the value of the analog voltage for each of the possible digital input code. So how will you do that? For each of the possible digital input code, that means my digital input code, if I write D2, D1, D0, it varies from 0, 0, 0, 1, 1. Yeah, these are the 8 different digital input word combinations. For every digital input word, we should find what is the analog output voltage, right? So as of now, from the given information, or we have no there is no information about any kind of non-linearity or error, because the possible way non-linearity can arise in the circuit is whenever there is a resistor mismatch. Now there is no information, so we are assuming that resistors from 1 to 8, R1 to R8 are equal and having value of 625. So you can easily find the value, right? For every for output voltage, you can find with the help of this. So how will you get the output voltage? V out is equal to the DAC output voltage, Vref divided by, so what is the output voltage of a DAC? V out is equal to, we have discussed it already. How will you write? The analog output voltage of a DAC. We have done it over here. So in general, we can write it is a fraction of reference voltage, and fraction is nothing but d by 2 to the power of n, right? So here, when you write that, d by 2 to the power of n into Vref. So can I quickly get the values here? Each output value from 0, 0, 0 to the last value. The first one, when the digital input word is 0, we are not expecting any increment at the output, so output will be equal to 0. What is the second value? It is 1 by 8 into Vref. So 5 by 8 closely is 0.625, and you will have all the other set of values, right? So next is 1.25, next is 1.875 plus 0.625, so it is 2.5, 3.125, 3.75 and 4.375. These are the corresponding analog output voltages. Alright, so what we have done here is, for a simple resistor string DAC, for a resistor string DAC with binary switch array, we obtain the value of the the output voltage for every input analog bit, right? So this is a simple one. Now let us look at this question where we have some more information given. The question here is, by the way, this is the tutorial question what is given. I think this is tutorial question number 1. Tutorial 4, which I shared today, the first question of that. The question given here is, there is a 3-bit simple resistor string DAC. So when you see that this simple resistor string DAC, what we can assume is there is no binary switch array. It is a simple switch, and that is designed with a desired resistor of 500 ohm. So we know that generally all the resistors what we use is equal. So in this specific question, it is given that the desired resistance value is 500. So in the example what we have done before, like 625 ohms, for this specific DAC, the expected or the desired value is 500 ohm. But after fabrication, due to mismatches, the actual value of resistors from R1 to R8, all these values are actually getting varied. So can you just give a try on this, how to find the solution for this? How will you go ahead with this? So whenever there is resistor mismatch, we can say that will lead to some kind of non-linearity, right? Because resistor mismatch means for every input digital code, digital word, we are expecting an output voltage. But now, due to mismatches, the output voltage will be deviating from the ideal value. So that will lead to DNL as well as INL. So let us see how to proceed with this. So are you guys with me? Can I get some response in the chat? Alright, yeah. So look at this. Now what is the reference voltage in this case? Here also it is given that the reference voltage is 5 volt. Reference Vref is equal to 5 volt. Vref is 5. Now, so since Vref is 5 and the desired value what we have for the resistance is 500, we can easily find we can find the current or the expected current in the circuit, we can get it, right? So how will you get it? Vref is 5. Now how can I write the total current in the circuit? Total current in the circuit can be written as the Vref voltage divided by the total current, the total resistance, R total. So what is R total? Single resistance value is 500. So 500 into 8 is equal to 4000, which is 4K. So 5 divided by 4K will give you the current in the circuit. And what is the current? 5 by 4K. What is 5 by 4K? It is 1.25 milliamp. This is the current. All right. Yes. So now, so what we need to find is, the resistor values are given. So we have to find the output voltage, and based on that we have to find the DNL and INL. The INL and DNL calculation also need to be done. So we can clearly see that the resistors R1 to R8 are deviating from 500. So if you look at this, R1 is 500, R8 is 500, the rest all the values there is a deviation, right? So there is mismatch. Now, so due to this mismatch, definitely all the when we tap voltage from every resistor point, the voltages, the actual voltage will be different from the voltage what we are expecting, right? So what we'll do is, now we know that, now we know the circuit, but let me just bring the circuit over here. We have the circuit here. So we have the circuit here. Now we'll find the output voltage, right? So what you can do is, this is not a binary switch array. So the digital input is in the form of from D7 to D0. So I'll write it as D7, D6, D5, D4, D3, D2, D1 and D0, right? Because we have to, there should be a logic to, there should be a control logic in order to directly give this bits in this form. All right, so now this will vary from all the way from 0, 0, 0 to till 1, 1, 1. All right. So this is the digital input. Now, let me just mark the rest of the things. So what we need to find is, we need to find the reference voltage, the voltage at every node of the resistor, the tapping from the resistance, and then based on that I need to find the output voltage, right? So let me write this as node voltage, where I have nodes varying from V0 to V7, right? So this is V0, V1, V2, V3, V4, V5, V6 and V7. Alright, so these are the node voltages. Which node voltages is the voltage at this point, right? What we are tapping from every resistor. Now, so what I need to write exactly here is, I need to know what is the actual output voltage coming in, and we can also calculate the ideal output voltage, and based on these two we can calculate DNL as well as INL, right? So two more columns I will write. One is the actual output voltage, V actual, which is in volts. Now another one is the ideal output voltage, V ideal, that is also in volts. Now if we have the actual and ideal output voltages, from that we can write this, from the actual and ideal output voltages we can find INL. Then if we can get the step height, the ideal step height and actual step height, we can find DNL as well. Alright, so I hope you guys are with me, you are listening and you are understanding what I am trying to do here. If yes, can I get some response in the chat? Alright, yeah. So there is one second. So this is not in this form. It will be what we have is of this, right? 0 0 0 0. All 0, then you have 1 at this position, then at this position, then here, 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 here and here. This is how the control, the digital, the switch control will be, right? Yeah. Now, so how will you get the actual output voltage? So actual output voltage can be obtained as, so for the initial when the digital input is 0, the actual output is 0, the ideal is also 0, right? This is 0, this is also 0, there is no difference. Now for V1 is this node voltage, right? So this node voltage is 5 into the resistance value R1 divided by the sum of all the resistors. Now look at the question once. So when you look at this question, you will get to know that let us also find sum of all the resistors. What is the sum of all resistors from 1 to 8? Yeah, that we have already done, right? The sum of all resistors from 1 to 5 is, when you can you sum up this and check what is the resistance value from 1 to 5? It is 4k, yeah. R from 1 to 8 is 4k. So what we can do is, for every node voltage, say for example, if I want to find V1 is equal to the corresponding resistor, which is R1 divided by summation of R into Vref. This is what the formula what we will be using, right? So based on this, we can actually get the actual output voltage. So we can write the actual output voltage depending on this formula. So can you quickly tell me what are these voltages, V1, V2 up to V7? What is V1 voltage? V1 voltage is basically the resistance value is 500 by 4k into 5. So what is V actual? (500 into 4k by 5). Yeah, it is 0.625. This voltage is 0.625. Now next is V2. So when you take V2, you have to take the sum of R1 and R2, right? Where R1 is 500, R2 is 480. So it is 980. So 980 by 4k into 5. Oh, it is 1.225. Yeah. Similarly, can I get the next answer? V3. What is V3? It will be 980 plus 470. Yeah, it is 1.8125. All right. And what is the next voltage? V4, 2.4625. Yes. And V5 is, yes, 3.1. V6 is 3.7125. And V7 is 4.375. These are the actual voltages. So actual voltages are calculated based on the fabricated resistor values which is given, which is having mismatch. Now how will you write the ideal voltage? So ideal voltage can be calculated easily by considering all the resistor values as 500, right? So that will be so 500 into 500 divided by 4k into VREF. In a similar way, same calculations we can do. So anyway, the first will be equal to 0.625, right? Because it is the ideal and actual value resistors are same. The remaining there will be small differences. So if we can quickly find that, we can tabulate it, and based on that we can do the rest of the calculation. Can I get the ideal values? One is 0.625. Yeah, it is 1.25. Yeah, it is 1.25. Then 1.875. It is 2.5. 3.125, 3.75 and 4.375. This can be, so to get the ideal value, once you write the first value, then you can actually add 0.625 to that, because ideally we expect uniform step height, right? So you can add 0.625 and then you can write the rest of the things. So you'll get the ideal values. Now the next step is actually to find the non-linearity. Non-linearity means both differential non-linearity and integral non-linearity. So what we know about these two non-linearities are, one is, so the differential non-linearity, so what we know about DNL is, DNL can be obtained if you know the DNL is obtained as the difference of the step height, right? So if you know the actual step height, and if we can deduct that from the ideal step height, what is the difference of actual step height and ideal step height will give you the DNL. So this should be done for every specific input digital word change. This is what we should do, right? Similarly, what is INL? INL can be obtained as a difference between the actual output voltage value minus the ideal output voltage value. This is what we saw. We told that we will be connecting the first and the last point. We will draw a line and we will see the deviation from this line. So if the actual is here and the ideal, and this is ideal, and this difference will give you the INL, the corresponding INL. I hope you understood this calculation of INL and DNL from the previous classes. So based on that, we will do calculations even here as well. So INL can be directly calculated in this case because the ideal voltage and actual voltage is available in the table form, right? Now to calculate INL and INL, we can directly write INL as V actual minus V ideal, right? And we can tabulate the INL. Now if you want to calculate DNL, we need to know the step height, right? So for that I am adding one more column here, that is for step height. Now step height also I have two things, one is the actual step height and another one is the ideal step height. So we can divide this column and find the actual and ideal step height. So how will you find the actual step height? For the first case there is no step height, so it is 0 and 0. Now the actual step height is this difference, right? This minus this difference is 0.625. In this case also ideal is also 0.625. Now for the second, the actual step height is 1.225 minus 0.625. You should write that value here. This to be filled with all the new values which need to be calculated, and this table, the ideal step height is 0.625 for all this input digital word. Alright, so can you tell me the values here which need to be filled for the actual step height? What are the values here? So actual step 1.225 minus 0.625. 0.6, right? This is 0.6. This is 0.6. Now 1.8125 minus 1.225, which is again 0.58, right? Yeah, 0.58. I think you can write up to 3 decimal place, 0.587. Then the next one is, can I quickly get the values? What is the next value? So from here to here, then this minus this to get this value, 2.4625 minus 0.6375. No, 0.65, right? Yeah, 0.65. Then 0.637. Then 0.6125. And one more. The last one is, yes, 0.6625. These are the actual step height. Now once this is there, you can directly report the DNL. What is DNL? DNL is we have the actual step height actual minus step height ideal. So this will give you the DNL calculations, DNL values. And for INL, we can write the actual voltage minus ideal. So we'll get the INL and DNL value. So this can be, you can try this. You can calculate and you can get the answers. So now, if you look at the question, you can see that determine the maximum INL and DNL for the DAC. So that can be obtained after getting all the values. So I can wait for maybe 1 or 2 minutes, just calculate the DNL values and INL values and see what is DNL max and INL max. Now this is 0, this difference is 0, this difference is actual minus ideal. So this is minus 0.025, actual minus ideal. This is 0.375. Yeah, if you can get me the rest of the values. That will give you DNL, and from DNL you can after DNL you can write the INL values as well. Yeah, the maximum the INL max is coming as 0.0625. all right, so INL max is 0.0625. Generally we write this in terms of LSB also. You can write in terms of volts, or even you can write in terms of LSB. So 1 LSB is 0.625. So this is 1/10 of LSB, right? Or this is 0.1 LSB. INL max is 0.1 LSB. So what about DNL max? DNL max. Yeah, INL isn't, yeah. So generally we write we write the magnitude of INL, and that maximum INL max magnitude should be within plus or minus 0.5, right? That is how we generally write. Yeah, DNL max is also there. So again, what I am writing is its magnitude, that is equal to so DNL max is 0.0375. So this also you can write in terms of LSB. So how do you write in this in terms of LSB? Yeah, you can write that in terms of LSB, right? So this is how we calculate or we solve the differential nonlinearity and integral nonlinearity of a simple resistor string DAC when all these informations are given now in this 0.06. All right, so this is equal to 0.06 LSB, right? Yeah, so this is how we can calculate the DNL and INL when all these informations are given. We know all the resistor values, we know the actual, we can calculate the actual ideal voltages and the step height, and thereby we can conclude, or we can comment about the comment about the differential and the integral non-linearity. All right, so I hope this is clear. If this numerical is clear, you can please respond in the chat box, and we'll continue. Are there any questions from this? All right, fine. So let us quickly look at the same resistor string DAC. Let us in little more detail about this INL and DNL and the worst case DNL INL in this resistor string DAC under the heading the mismatch errors, that is basically INL DNL in this resistor string DAC. Through the numerical we solved it, we got it, how to do it. Let us look in a little more detail way. All right. So we know that when we use a resistor string DAC, whether it is binary switch array or a simple resistor string DAC, the accuracy of the resistor string is related to the matching of the resistors, right? So all the resistors should be equal. In this case, in the first numerical, we saw that we have taken all as 625. Then the ideal and the actual values are, there is no difference between ideal and actual value, but it was same. But Durgesh, I think you have a question. DNL max is minus 0.038. Yeah, the magnitude is 0.03, correct. What did I write? Yeah, 0.0375. Both are same, right? If you are asking for the polarity, what I have written is here. So the differential non-linearity, the non-linearity is from the deviation from the ideal, right? So in certain cases it is going, if the actual value is more than ideal, it is positive. If it is other way, it is negative. So in general, for a DAC, how do we talk about the maximum DNL or INL permissible is if it is coming within the range of plus or minus 0.5 LSB, right? So generally we write it as a magnitude. Yeah, fine. Alright, so coming back to this, what I was trying to say is the accuracy of the resistor string is directly related to the matching between the resistors. All resistors should be of equal value, but that is not practically possible, right? Now, say for example, we have many number of resistors. Say for an n-bit DAC, n-bit DAC, the resistor will range from, the resistor value will range from say 1 to 2 to the power of n, right? When I number the resistor, for example, I'll use this notation as I, where I, the range of I is from, I ranges from 1 to 2 to the power of n. We call it as R1, R2, R3 up to. If it is 3-bit DAC, we'll talk up to R8. Otherwise, it will go up to the maximum number of the 2 to the power of n value, right? Now, say for example, that means let me use, yeah, for an n-bit DAC, there is R value will vary from 1 to 2 to the power of n, right? In that, say if there is an resistor, I'm just calling it as ith resistor. If the ith resistor, I'm calling it as Ri, if this is having a mismatch error, assuming that the ith resistor is having a mismatch error. So what do you understand by mismatch error? Ideally the value of the ith resistor should be equal to R. R is the ideal value. Say for example, if R is the ideal value, but due to mismatch, the ith value is not R, but there is a mismatch, and that mismatch I am writing it as delta Ri. Right. So what do you understand from this? This is actually the ideal value. This is the ideal value, and this delta Ri is due to the mismatch error. This is due to mismatch error. Now, we make one assumption here. that was even true. That was true even in this the previous example what we have done. Suppose that we are assuming that the mismatches were symmetrical about the string. When I say symmetrical around this about the string, the meaning is sum of all the mismatched terms from the resistor number 1 to resistor number 2 to the power of n, that sum I am assuming it as 0. Just for the calculation easiness, what I am doing is I am just assuming that mismatches were symmetrical about the swing. Right. So that is an assumption what I am making, assuming that mismatches are symmetrical about the string. That means if ith resistor is having delta Ri as a mismatch error, now the sum of all the mismatch errors, that is from I equal to 1 to I equal to the power of n, that sum is equal to 0. That means sum of all the mismatches in the resistor string DAC is equal to 0. Right. This is one assumption what I am taking. Now what I want to do here is I want to know what is the So what I want to know here is I want to write the ideal voltage that can be tapped at the ith resistor and the actual voltage that can be tapped at the ith resistor with this mismatch error, so that I can come to a generalized formula for the calculation of INL and DNL. That is what I am going to do now. Right. So now if I write the voltage tapped at the ith resistor, voltage tapped at the ith resistor, I'll write the ideal voltage, the ideal value of the voltage tapped at the ith resistor. How can I write the ideal voltage tapped at the ith resistor value? That can be written as, in general we write it as Vref divided by 2 to the power of n, right? So Vref by 2 to the power of n. No, how can we write this? In the previous case, how did we write? It is R1 divided by sum of all the resistors from R1 to R8 into Vref. This is how we have written the ideal expression. Correct, no? So now this can be, when I generalize this, what I can do is I can write this as say this I, the value is I, which is varying from 1 to 2 to the power of n, I divided by 2 to the power of n into Vref, where the value of I will change from 1, 2, 3 up to 2 to the power of n. Since I am writing the ideal voltage, the resistance values are same, so R can be cancelled out. So that is how I can write it as I by 2 to the power of n into Vref. Whether this is clear, what I have written as the voltage tapped at the ith resistor as ideal, whether this expression is clear? Can I get some response? So what I am going to do now is I am just arriving at a generalized expression for the calculation of nonlinearity of this DAC, both INL as well as DNL. Right. For that, what I have done first is I'm just assuming an n-bit DAC. In that n-bit DAC, all the resistors will have mismatches. I am assuming that all resistors have mismatches. So if I am considering an ith resistor, that mismatch error I am including as delta Ri. But one assumption for the calculation purpose, what I am doing is, if I consider the resistor string DAC as a whole, the sum of all the mismatches I am considering it equal to 0. Later we can add that. So sum of all the mismatches I am considering it equal to 0. In that case, I am going to write the ideal voltage that is tapped at the ith resistor and the actual voltage which is tapped at the ith resistor, and through that I can write the INL value. Alright. So can I get some more response regarding the expression what I have written? If you have questions, please put it in the chat box. Now similarly, what I can do here is I can also write the voltage which I am tapping at the ith resistor, which is the actual voltage. So when I write actual voltage, the meaning is with mismatch, including mismatch. Yeah, so and so on. I am taking the value of I from 1 to 2 to the power of n, because previously also I numbered it like this. Resistance values I am numbering from R1 to R8. Or otherwise, okay, you have written from 0 to 2 to the power of n minus 1. Yeah, both are same only, right? Yeah. So now looking at this, yeah. So with mismatch, the actual value of the ith voltage can be written as the sum of all the resistances up to that ith node divided by the sum of all the resistors in the string, right? So when I write the actual voltage, how can I write here is, this can be written as, in place of I, what I will do is, I will write it as summation of k equal to, I am just taking k varies from 1 to I, because what I am writing is the voltage tapped at the ith resistor. So what I need to do is, if I want to find the actual voltage, the numerator will be sum of all the resistors up to that term, right? Maybe I will just take a simple example here. Say for example, I want to find the voltage at this node. What I will do, if all these 3 are R, what I will do, I will write it as 2R by 3R into VRF. I have just taken a generic example. This is not in relation with any DAC. So this node voltage is 2R divided by 3R into VRF. So in ideal case, this RR will get cancelled. So it is just 2 by 3 into VRF. Now, but when there is mismatch error, how can I write this node voltage? It is 2R plus the mismatches there, right? So mismatches are, should be taken as delta R value divided by sum of all the resistors. And based on my assumption that mismatch in total mismatch is equal to 0, so denominator will be only equal to 3R. Right, this is the logic what I am taking to write it here. So how will I write it here? Summation k from 1 to I, because I need to tap the voltage from the ith resistor, so I need to calculate the sum of the resistors from bottom up to I. Right, so this one, and I am just putting it as Rk divided by this summation. I will change from k equal to 1 to, this is from 2 to the power of n of Rk into VRF. This is how we can write it. Is this expression clear? Yeah, this is simple only. I am just trying to bring up a generic expression. Now this can also be written as, yes.
The voltage tapped at ith resistor doesn't mean V0, right? Or V0 is always 0. This is
V0 is always 0. Yeah. The first one is always 0. Yes.
Okay, sir.
Yeah. Now this can be further written as, now if you look at the numerator term, especially if you look at this term, here k is varied from 1 to I of Rk, but in this there is mismatch, so we need to account mismatch in the numerator term, right? So how will I separately write that? I can write this as summation k equal to 1 to I, that resistance value, if I am considering it as R plus delta R k. Alright. Summation k equal to 1 to I. R is the actual resistance value which varies from 1 to I plus the delta R k divided by this becomes 2 to the power of n into R. There is no mismatch component there, so I'll have 2 to the power of n into R. Right, is this clear what I have written? Let me take this expression to the next page. Alright, now this can be further written as, so this is the actual voltage, so V actual can be further written as, I think I forgot to put, yeah, there is V ref here. This can be further written as V ref divided by 2 to the power of n into R. And what is there inside? Summation k equal to 1 to I. So that will give you I into R plus the next summation, that is summation k equal to 1 to I of delta Rk. This is how we can write this expression. Or if I further break up this, I can write it as I into, I am just opening this bracket, so I into V ref divided by 2 to the power of n, because R and R will cancel, plus V ref divided by 2 to the power of n into R into the summation term k equal to 1 to I into delta Rk. This is V actual. Right. Now, if you look at this term, we look at the final expression what I have written. See this. Here we can see that this term what I have here, I into V ref by 2 to the power of n, this is nothing but the ideal voltage. Right. So, I can otherwise write it as V actual is equal to V ideal plus V ref divided by 2 to the power of n into summation k equal to 1 to I delta Rk divided by R. There is an R in this denominator, so that I have written inside this. Right. So directly this expression, or we know that integral nonlinearity is nothing but the actual voltage minus ideal voltage. So I can say that INL is equal to V actual minus V ideal is equal to V ref divided by 2 to the power of n into summation k equal to 1 to I delta Rk divided by R. This is the generic value of the expression for IN. Alright, so what we do is we will continue this. We need to look at the worst case scenario by considering the mismatches. That will continue in the next class. So if you have questions, any questions till this, we can discuss that now.